and welcome to HashiTalks 2024. My name is Hamza, and I'll be talking about how we helped a retail giant in the mattress and sleep essentials industry to deliver resiliency with GCP Cloud SQL via Terraform. We'll discuss what GCP's Cloud SQL offering looks like, its features, configurations, potential pitfalls, and finally finding success in automating it all with Terraform. First, a little bit about myself and Risha. I'm a cloud architect and co-founder at Risha.io. We're a DevSecOps consulting firm based out of Toronto, Canada. We serve customers in the government, retail, banking, and telecom industries. Databases have historically played an important role. Whether you're online shopping, using social networking sites, or watching your favorite show on Netflix, databases allow your information to be stored in a persistent storage. But as long as databases have existed, we've had the age-old problem of ensuring our databases are resilient, always available, and secure. The origins of the first relational database trace back to the 1970s, and you'd imagine we must have learned a lot in those 50 plus years. Well, we haven't. Databases are complicated, and with the advent of cloud providers, we now have managed databases which have taken away a lot of the overhead of managing a database yourself. Let's talk about GCP's Cloud SQL database. Google Cloud characterizes its Cloud SQL service as a comprehensive, managed relational database service. Cloud SQL encompasses three major offerings: MySQL, PostgreSQL, and SQL Server. The managed database offering reduces maintenance overhead, automates database provisioning, storage capacity management, replication, and backups. It offers standard connection drivers and built-in migration tools. Setting up your Cloud SQL instance is easy. You select the region and the zone you would like your instance deployed to, and it provisions it for you. With GCP's wide range of regions and zones, customers are able to deploy their persistent storage layer close to their end users and make best use of their data. You also have a range of configuration options where you can select machine type for configuring the virtual CPU and memory, storage type for configuring solid state or hard disk drives, depending on whether you want low latency or low cost, and storage capacity, where higher storage capacity leads to better performance. In addition, you can automatically increase storage when nearing capacity. By implementing auto-scaling in Cloud SQL, users can ensure that their databases have the required storage capacity to handle varying workloads and growing data demands efficiently. This automated approach simplifies the resource management, allowing developers and administrators to focus on building and optimizing applications rather than manually adjusting storage sizes. You can ensure your data is encrypted both at rest inside Cloud SQL and in transit when communicating with your end user. Cloud SQL employs robust encryption measures to safeguard data both at rest and in transit. For data at rest, Cloud SQL uses Google's Transparent Data Encryption, or TDE, ensuring that stored data remains encrypted on disk, mitigating potential security threats. In transit, data is secured through industry standard encryption protocols, employing transport layer security, or TLS, to establish secure connections between clients and Cloud SQL instances. This end-to-end encryption safeguards sensitive information during transmission, reinforcing the overall security posture of Google Cloud SQL and providing customers with a secure environment for their relational database. Cloud SQL offers a robust and scalable relational database service, providing seamless data ingestion capabilities from various sources within the GCP ecosystem and external applications. Cloud SQL seamlessly integrates with App Engine, allowing applications hosted on App Engine to connect to Google Cloud through Cloud SQL databases directly. This integration provides a straightforward method for ingestion and managing relational data, ensuring consistency and reliability. For applications running on Compute Engine, Cloud SQL serves as a relational database solution that is ideal in the cloud. Compute Engine instances can establish secure connections to Cloud SQL, enabling efficient data ingestion, storage, and retrieval. This integration ensures the scalability and performance required for diverse workloads. Cloud Run, with its serverless container environment, easily connects with Cloud SQL for data ingestion. Containerized applications deployed on Cloud Run can leverage Cloud SQL as a relational database backend, ensuring that data ingestion is seamless and well integrated into the serverless architecture. Kubernetes Engine, as a container orchestration platform, can deploy applications that utilize Cloud SQL for data storage and retrieval. This integration ensures that Kubernetes managed containers have access to reliable and fully managed relational database, streamlining data ingestion for containerized workloads. Cloud Functions serverless compute service can trigger events that initiate data ingestion into Cloud SQL. This event-driven architecture allows for seamless execution of functions that interact with Cloud SQL, enabling dynamic and responsive data processing. Cloud SQL facilitates data ingestion from external applications through standard database connectivity protocols. External applications can ensure that there's a secure connection to Cloud SQL, enabling the seamless transfer of data between on-premise systems or other cloud environments and Google Cloud SQL database. Cloud SQL's versatility in integrating with various GCP services and external applications ensure a unified and efficient approach to data ingestion. In essence, Cloud SQL takes care of your databases, allowing your business to operate seamlessly without interruptions. But is it a really fully managed service? Let's take a look. In essence, if a client asks you to productionize a Cloud SQL database, initially there are four main categories you would likely consider when building a resilient database. Replication, which would allow you to offload some of the work to copies of your database. Backups, whether they are automated or scheduled, you would need a proper mechanism to trigger a point-in-time recovery of your database. High availability to provide data redundancy and protect your deployment against a zonal outage, and disaster recovery. In case an entire region goes down for your cloud provider, you'd ideally want a regional failover instance you could fall back on. If you follow the GCP Cloud SQL wizard to deploy your database, it might seem pretty straightforward to get a Cloud SQL instance deployed. Unfortunately, databases don't work in complete isolation. They require connection to the source of data through a secure channel. They require maintenance windows for upgrades, authentication to allow users to log in, and logging and monitoring to keep track of performance and availability. It's easier to see why things can get complicated while setting up a database. As businesses grow, the volume of data they generate and manage also increases. Ensuring that a database system can scale horizontally or vertically to handle this growth without compromising performance or reliability becomes a critical concern. Scaling databases while maintaining consistency and minimizing downtime is a complex task. Achieving optimal database performance is a constant challenge. It involves tuning database configurations, indexing strategies, and query optimization. Balancing the trade-offs between read and write performance, minimizing latency, and optimizing storage are ongoing tasks that require careful consideration. Databases often store sensitive information, making security a top priority. Implementing robust authentication mechanisms, encryption protocols, and access control is crucial. Regular security audits, vulnerability assessments, and compliance with industry regulations add layers of complexity to database management. Authentication and authorization for federated users and applications require detailed attention and often become a key component in ensuring your business's integrity. There's quite a few examples of businesses being in the news for leaking confidential information due to a lack of controls in place. Establishing robust backup and recovery strategies is vital to safeguard against data loss or system failures. Determining the frequency of backups, the appropriate recovery point objectives or RPOs, and ensuring a reliable disaster recovery plan contribute to the complexity of managing databases. Database management systems are continuously evolving to address security vulnerabilities, enhance performance, and introduce new features. Staying up to date with the latest software releases and patches while ensuring minimal disruption to ongoing operations requires careful planning and execution. Even though cloud providers offer managed databases, businesses still need to be mindful of scheduled downtimes to allow their databases to catch up on latest releases and patches. In many organizations, databases need to interact with other systems and applications. Ensuring a seamless exchange between databases and different software components, especially in heterogeneous environments, can be challenging. Integration with third-party tools and technologies further complicates the landscape. Continuous monitoring of database performance, resource utilization, and query execution is essential for proactive issue detection. When problems arise, identifying the root cause and implementing effective troubleshooting strategies requires a deep understanding of the database system and its interactions with the overall infrastructure. Deploying and managing a database is a multifaceted task that demands expertise in database design, performance, optimization, security, and ongoing maintenance. The challenges arise from dynamic nature of data, the need for scalability, security considerations, and the diversity of database technologies. That being said, our client, as most clients would, required a resilient architecture, prioritizing all the bells and whistles. And after going on this journey of finding the most resilient cloud SQL architecture, we finally arrived at an architecture that satisfies all the requirements. This slide looks pretty complicated, so let's break it down. Starting from left to right, we have Compute Engine, Cloud Functions, and Cloud Run, which are all possible sources for writing and reading from our Cloud SQL database. To the right, we have two options. First, we have VPC peering, which uses private services access to allow VM instances in your VPC network, and Cloud SQL to communicate exclusively by using internal IP addresses. Second, we have GCP's serverless VPC access connector, which allows sources like Cloud Run and Cloud Functions to communicate with GCP Cloud SQL using a private IP. As you can imagine, this is a pretty important step in ensuring our source and destination communicate over a private channel and avoid traversing the public internet. Once a request passes through and reaches GCP's private network, we reach a static IP address for the primary GCP Cloud SQL database. Now, in order to ensure not all transactions are processed by the primary instance, reads can be served by replicas. This ensures the primary instance only processes critical writes or reads as part of transactions, improving the performance of the database and the application. So naturally, we have some read replicas deployed. The first read replica is deployed within the same zone as the primary database. The second read replica is a zonal read replica in an adjacent zone within the same region in order to protect us against a zonal outage. This covers replication. In order to tackle high availability, we have a cold standby instance in the adjacent zone where our zonal replica instance was deployed. As you can imagine, if we had a zonal outage, our standby HA instance would take over, and we would also have a read replica available to offset any spike in traffic. One cool thing about this setup is that GCP offers regional persistent disk. All writes made to the primary instance are replicated synchronously to disks in both zones before a transaction is reported as committed, providing data redundancy. And finally, for disaster recovery, we have a cross-region read replica which protects us against a regional outage. In case of a regional outage, we can promote this replica to become its own primary database instance. So let's talk about Terraform structure and how we can break this down into simple, reusable components. First up, we have networking. We can create a separate folder or module for our networking components. In most cases, organizations use these to deploy and configure their VPCs, subnets, firewalls, and all things related to the network. In our case, we're doing something similar by deploying VPC, subnets, a private IP address, and then our two components that allow us to communicate with Cloud SQL over private IP. Diving a little bit deeper, the VPC peering connection requires the private network we are creating above this, a provider peering service, aka the service networking API, and some reserved peering ranges. The serverless VPC access connector requires a project, region, and the subnet it will reside under. Quick disclaimer, these components serve as a prerequisite for deploying our Cloud SQL database. Next up, we have Cloud SQL. First, we're looking to deploy our primary database instance. For our database, some of the key configurations include setting the tier, disk size, and type, pricing plan, whether we want high availability and auto resizing in case of capacity issues. After that, we set some of the database flags. These allow us to enable audit logs, IAM-based authentication, and enforce how many max connections we would like. For backup and maintenance, we create these dynamic blocks which allow us to configure nested objects within a Terraform resource. So in this case, to configure backups, we configure nested fields like point-in-time recovery, when to start taking backups, where to store them, and the retention period. We also have a dynamic block for maintenance windows, which allows us to set up the day and hour in a given week to apply patches and upgrades to our SQL database. Next, we have some networking and insights configuration. In the first dynamic block, we pass configuration for setting an IPv4 address, the private network we created previously through our network module, and enforce SSL connections to the database. The require SSL is an important field to enable, so we can guarantee a secure connection between our source and destination. Inside the location preference block, we set the zone for our database. And finally, in the insights config block, we pass arguments for what sort of insights we would like to collect from the database, like the application tags and client addresses. That's all for the primary database instance, but we would like to set up a database inside our Cloud SQL instance and an IAM authenticated user. The database is simple to set up and requires basic information like name, project ID, and a reference to Cloud SQL instance. The IAM user requires the user's email, the Cloud SQL instance reference, and the type. When you use an IAM account to connect to Cloud SQL instance, the account must have the Cloud SQL client role, which includes the permissions required for connecting. A quick disclaimer about IAM users. An IAM user by default will not have any permissions within the database. An admin user has to grant an IAM user permissions on the specific database to read and write. It's also important to remember that if you have the require SSL flag set up on the database, all IAM users and service accounts have to provide the necessary certificates in order to authenticate. Finally, we have replicas. So this is an example of one of the replicas, but both the other replicas are set up the same way, except one is deployed in a different zone within the same region, and the other is within a different region altogether. That being said, a replica instance requires configuration for region, database version, and deletion protection. Some instance-specific configurations include passing a database flag for max connection, setting availability type, disk size, backup configuration, IP configuration, and the location preference. Lastly, you need to pass a reference for which master instance name the instance will be a replica for. An important thing to mention here is that GCP claims that in case of a zonal outage, your HA or standby instance can automatically take over as a primary database, maintaining the same IP address and connection string to ensure that all connections to the previous primary database instance are seamlessly transferred over to the new primary database. The same does not apply for a regional outage. In our solution, even though we deployed a cross-region read replica, which would have asynchronous replication from the master database instance, in case of a disaster, we would have to manually upgrade the cross-region read replica to primary database instance status. This process is documented in several places and can be scripted with Terraform outside this current setup. And that's it. With all those pieces put together, we get our resilient Cloud SQL architecture deployed via Terraform. Migrating to Cloud SQL from an on-premise environment empowered our client with unparalleled benefits. The seamless transition provided scalable and fully managed relational databases, eliminating the complexities of on-premise maintenance. The client experienced enhanced performance thanks to Google Cloud's advanced infrastructure. With automatic backups, high availability, and global replication, data reliability reached new heights. Moreover, the pay-as-you-go model optimized cost, ensuring efficient resource utilization. The migration not only future-proofed their database infrastructure, but also unlocked agility, enabling the client to focus on innovation rather than managing on-premise complexities. This process got streamlined through the strategic use of Terraform automation. Terraform played a pivotal role in orchestrating the entire migration process, allowing for seamless provisioning and configuration of cloud resources. The client leveraged Terraform's capabilities to define, deploy, and manage their infrastructure on Google Cloud. This automation not only expedited the migration, but also ensured consistency and reliability, enabling our client to efficiently manage and scale their Cloud SQL environment while minimizing manual intervention. So with that, thank you so much for tuning in to my talk today. I'll be in the comment section after this to answer any questions, and you can reach out to me via LinkedIn or email if you'd like to discuss all things DevOps. Thank you.